Might as well get going. I don't think anybody else is going to show up. What I'm going to do today is try to go back to where we left off when we started the business on image processing. I went through it far too fast last time. And I want to spend a little more time on it so anyone who has a PC has an opportunity to figure out, by hands-on, what to do. I want to make sure you understand that there's another session next week that will talk about how to do astrophotography in light polluted skies. It's going to involve talking about the method I came up with the same configuration I showed you in the images, with a DSLR mounted on a Teleview 85 and taking relatively large field of view, how to extract the light pollution from the image and be left with only the image itself. The other half of it is going to involve Dave Nakamoto. He has another method he came up with using a very narrow field of view camera that is a different way to go about it. His method has some advantages in the sense that the field of view is so narrow, the likelihood of having light pollution gradients is much less. With what I've been doing, the light gradient is a big problem. And so he'll talk about his method, I'll talk about mine. You're welcome to come, even if you feel like you're not going to understand it, because I can tell you right now, the method that's involved takes a great deal of processing, far beyond anything we're going to be talking about today. But it's useful information that you might find fun.
I think the comment I'll make is what Dave is doing. I think it's similar to the Takahashi system we got out at Lockwood Valley with the, I think the S-Big camera. Is that a narrow field of view?
It is, but it's bigger field of view than his camera.
Oh, okay.
Not by a lot, but it is a bigger.
Make that comment that,
yeah,
that at least that perspective, you're coming from two different perspectives, and I think the S-Big out there is similar to what he's got.
He's using a. I'm sorry?
Maybe you could videotape the session next week.
Oh yeah, if Ray is willing to do it,
yes.
that'd be good.
If you get that video, that would be wonderful.
Okay, now there's one other thing I want to mention, and this is something that's new in the club. You know about the 60-inch nights that have been set up, and these are all, you got about 25 people there typically. It's all visual. And it's a lot of fun. Believe me, I've done many of them because they're so neat. On October 28th, that's a Friday night, we are putting together a session for 10 people maximum. We're going to do imaging on the 60-inch with whatever camera you've got. Now, most of us are going to be going up there with a DSLR. Some people might bring up something else, thermally cooled CCD camera or whatever. I've got one. I might bring it up. Huh? 28th, October 28th. It'll cost $95 a head because there's only 10 of us, so we got to foot the bill. It will be, unless we are rained out or something like that, a spectacular opportunity. I've seen some of the stuff people have done through the 60 with today's imaging equipment, and it is truly spectacular. So it's an opportunity to play with something that not only is historical, but is a huge aperture that can really do some interesting things.
What I have now is field, or the T adapter and with a field flattener on it. It's kind of built in.
So if you can't get the field flattener out, I'll bring one for you.
Okay.
Because you don't need it with that monstrosity. The field curvature is such a large radius. We've got a 28,000 millimeter focal length. Okay, the radius of curvature of the curved field is so huge that your chip is going to be insignificant by comparison. Okay. Anyway, I've got a couple of available, at least for Canon.
Canon it is.
Session 4 on the Blue Skies, is that on this DVD, or are you going to burn another DVD for us?
Wow. You have the data files for it.
It's on there.
Is it?
Yeah,
We
the
have
files,
data files, but not the presentation.
presentation is sort of irrelevant in the sense that the data and the processing method I described is the most important. The data is is going to give you an opportunity to actually see what it looks like. I don't want to go into it now because I don't want to waste time that we want to spend here for this other business. But anyone who wants to sign up for this October 28th session, I have a list I'm making here. So just be aware that it's there. I'm going to send out an announcement to the rest of the class as well. And hopefully if others want to join, they can. But the limit is 10, of course, because we want to have time for everyone to get imaging done. And what's going to happen is we're going to have a session here the Wednesday before to talk about what objects we're going to shoot and who's going to shoot what, so we can schedule things optimally. We only have half a night till 1 a.m. So we've got to make good use of the time. Okay, any other questions or discussion at the moment? All right, let's move on, start this thing. What we talked about last time was, I kind of glossed over this, but the business with using a fixed camera and a tripod is something we need to talk about a little bit for the image processing. Fortunately for that, you're not going to be taking sub-exposures, so you don't have to stack and align and everything like that. So that's easy. In fact, you don't even have to use raw images. You can use JPEG images for this, because the amount of adjustment you can do is relatively modest. That's not to say you can't do sub-exposures and stacking. It's much harder to do on a fixed tripod because things are moving. Your maximum exposure is going to be about 30 seconds. You take the next exposure and the next exposure is moved relative to the first, and so on. So the field is drifting across your camera chip. Not a good thing. So a sequence of JPEG images can be strung into a video. That's fun to do. I recommend you try that sometime. For that, you need a 15 to 18 millimeter lens, wide angle lens, to do that really nicely. And we'll talk about what processing we want to do here. Camera on a tracking platform or a go-to mount, that's where you start to get into the multiple sub-exposures business. And we have Deep Sky Stacker as the tool that we use for assembling the sub-exposures into a single final image. There are lots of other tools available. Most of them are very costly. Some of them are intermediate priced. You can look into them. I can tell you some of the things that are available. So you can think about it. You're going to do some nonlinear stretching to bring out details. That means if there's any scientific value you wanted in there, it's gone after the stretching, because you're going to mess up the linearity of the illumination effect on the chip. But we're building pictures, not scientific images. And make some color and contrast adjustments can be done in GIMP, but we're going to run into problems with that in part because GIMP can only have 8 bits per pixel, or 8 bits per channel digitization, and you really need 16 to do the kind of thing we're talking about. And you'll see what effect that has, having only 8 bits in just a bit. For the tripod images, you start out with short exposures. You look at the histogram, and most of the data is down at the low end, because you're only taking a 30-second exposure, a long way from the dynamic range of the chip. The only thing you really want to do here is kind of darken the background a bit and boost the brighter part of the image a bit, just to make it pop a bit. You can't do a whole lot. As a result of the fact that you can't do a whole lot, then doing it with an 8-bit limitation is not a problem. So you may or may not be able to make this out in these 2 small images, but that's the image that's open, and this is the one that's been adjusted with curves a bit. And all that's doing is you can see the region here is a little bit brighter than here in the sky. And the Milky Way stands out just a little bit more. You can play with it more. You can do whatever you want. And you can do it all in GIMP, and it'll typically not result in images that are going to be compromised by the digitization. Okay, so now this is the heart of the session today, talking about what to do with images that come in the form of multiple sub-exposures of exposure times ranging from at least 30 seconds to 6 minutes or so, depending on how much you can push your camera to produce images without too much thermal noise. DSLRs, if you go much past 4 minutes, you start having a lot of pedestal building up that's thermal noise. And at some point you're going to just run out of dynamic range and you're not going to be able to get anything reasonable out of it. But you play with your particular camera to find out what your limit is there. Okay? The other thing that's important is you have to have calibration images. You have to have a dark frame to tell you that's done at exactly the same exposure time as the sub-exposures. The dark frame gives you information about the thermal noise that the camera is producing. You take about 10 of those dark exposures or more, and the software will average them together and produce what's called a master dark. That in turn is subtracted from the sub-exposures before you do any further processing or stacking. There's a flat frame, and that I explained briefly is you put a diffuser over the aperture of your lens or your telescope, and you make it dense enough that you can take relatively modest exposures of the order of a couple of seconds using the twilight sky before it gets dark. And what you want to shoot for is to get the flat frame to give you the information about vignetting in the lens system, dust motes that are on your camera that'll show up as kind of hazy circular features. Okay, that in turn is averaged in the software, and then you get a master flat frame. That in turn is computationally adjusted by effectively dividing it out. It's normalized so that the average is 1, and so the numbers range between slightly less than 1 to greater than 1. You effectively normalize this correction into the subframes. So you end up removing the gradient caused by vignetting and removing the ghostly images of the dirt that you have on your camera chip. Okay? Then there's a thing called a bias frame. A bias frame is a special case. When you take a picture with a digital sensor, you will get a certain amount of noise from the reading process and a certain bias that's applied by the camera itself. DSLRs are notorious for doing that, and you need to compensate that out. Okay? And that's just a short exposure with your lens cap on, dark image, 125th second exposure, short exposure, 1,000th of a second, whatever. We want it to be short enough that you don't accumulate any significant thermal noise, but you want to capture that bias noise. Now, those three are the basics. There are others. There are about 2 other corrections you might want to consider as you get further into this. It's beyond what we're going to talk about today.
Vance,
Yes.
I should tell them what happened to me when I was doing my flat frames.
Sorry?
What happened to me when I was doing my flat frames.
Oh yeah, that's
Yeah.
a gotcha.
Yeah,
He built a really nice flat frame box. I mean, a lot of people do that.
with EL.
And an electroluminescent panel and diffusers so that it's perfectly uniform illumination over the aperture. You slip this thing over the camera, and he took a whole bunch of flat fields, and they came out black. Why in the heck would they come out black? Well, there's some settings in the tools that effectively set the black point and the high point exactly the same.
Right.
So the image was black. Once he found out what his
Yeah.
glitch was, all of a sudden he had perfect flat plane.
Yeah.
Okay, so those kinds of gotchas will
Move a little
sneak up
curve
on
out
you.
to the left, and you got, it's your stretch, the stretching thing.
Yeah, yeah.
Just move it out and.
Well,
go off
different
it.
tools will have different
Yeah.
different ways of dealing with it. Yes.
What's the purpose? I think last time you said the flat frame should be taken straight up.
Well, if you're going to use the twilight sky, yeah.
Yeah.
If you're going to have what he has, which is a flat
Yeah.
illuminator, it doesn't matter which way you point it.
No.
It's going to be, the reason you point it straight up is just convenience, so that you can put something on top of your lens. Sir.
You get away without putting a diffuser on if you just have, there's no clouds in the sky and it's twilight and it's pretty.
A lot of people have done that. You know what's wrong with that?
Stars.
Stars will pop out of that. You know, you can look through binoculars and you can pick up the planets in the sky if you know where to point the binoculars, but you can't see them with your eye. So a big aperture is going to concentrate star images even in the bright sky. So you want a diffuser over it nonetheless. There was a big discussion about that about 15 years ago. And everybody finally agreed, yeah, sky flats are a bad idea. They just don't work. There's just too many variations that occur that are natural to the sky. So everybody says, well, use the t-shirt idea. Well, that's one thing, but there's also even better, more Lambertian plastic sheets you can buy for not very much money that'll do a better job. Okay?
So the flat frame is to capture the natural distortion of the image.
No, it's to capture the vignetting. In other words, the non-uniform illumination. If you take a picture of a blank sky with your camera, you look at it very carefully, you'll see the corners a little bit darker than the center.
Yes.
And that's because the optical system is cutting off part of the light cone going through the system as it goes to the corners of the imager. Now, when you get into deep sky work like this, and you're going to be doing some huge dynamic range stretches, and that vignetting will suddenly become extremely apparent if you don't remove it. Okay? The other thing is the dust motes that occur. In other words, you have a little bit of dust on the glass that's between the lens and the sensor. The dust won't show up as anything but a diffused shadow. And the flat frame will get rid of that. So you do the flat frames after you've got your camera attached to your telescope. Don't do it. Don't take the camera off and put it back on and then take a flat frame. Theoretically, you can do flat frames anytime you want. But it's the wrong thing to do. You want to capture that moment's dirt. Okay.
What is it better where to focus?
Sorry?
What is it better where to focus?
It should be at focus, as close to at nominal focus as possible.
Okay.
Because that affects how the dust motes are represented by the light cone coming in.
Thank you.
Okay, so for this class we're using Deep Sky Stacker. As I said, there are other tools, many other better tools than that. This one's free and it's pretty good. The problem with this Deep Sky Stacker is when you do the stretching, there is no real-time feedback. And most of the other tools do have that, and that's very, very helpful. But you can't beat free for a price. And GIMP, as I said before, is fine when it comes out with a 16-bit per channel version of it. For now, it's marginally useful. Okay. So, the opening frame on the Deep Sky Stacker is this. There are some controls along the left edge of the screen. The bottom of the screen will serve several purposes as you go along. When you're loading the images, there'll be a list of images there that you've loaded. Up here is a slider that controls the contrast of the image presented on this middle part here. That does not affect the actual digital image. It only affects what's displayed. This is helpful when you have an image that's kind of difficult to make out as it comes off the camera. So, you can play with that. I typically don't, but it's up to you what you want to do with it. So the first thing you're going to do is you're going to open picture files. You go to the folder that you click on this, and it'll present a pop-up window, and it'll tell you, you'll navigate to your folder that contains the images, and it'll be presented as a list of images. They're all your sub-exposures. And then we're going to go down. The next thing is to get the dark files and the flat files and the bias files if we're going to use them. We don't have to, but we can. This offset and bias files is what the bias files are. Notice it says dark flats. If you really want to be fussy, you'll do that too. Because keep in mind, the readout is the same whether you have black image or light image. The readout noise is going to be there no matter what. So if you want to be really fussy, include the flats, the bias files during the flat field data. I don't most of the time, and the images come out pretty well. But again, depends on the way you want to run things. So we get on the list one at a time and pick up everything, and we finally end up with capturing an image. We go in, and I'm going to show you this in a minute. You'll double click on one of the pictures that you have in the image file lists. It'll bring up that image on this viewing area. What I'm trying to show you here is you take your mouse pointer and get it pointed right at one of the stars, and you'll see very highly magnified star image. And you go around and check a few stars to make sure you haven't misguided something. And you use that as the basis for selecting images you're going to stack versus the ones you're going to reject.
Be careful with double stars.
Yeah, well, I mean, that's why you want to go and look at a bunch of images, because you'll know with the double star it's pretty obvious when you figure it out. If you have a star in the middle of the field that looks elongated, and you go a short distance away and click on another one, and there's not out around, then you know it was a double star, close double. And that's pretty simple. And there's a item here that says check all. The images, when you load them into DSS, come in a list and they are unchecked. Any image that is unchecked is not processed. So it gives you an opportunity to go down the list, find all the images that are good, click on the little box to the left of the image. That's the one you're going to use. The one you don't want to use, you don't click, and so forth. I find it easier to click all and go down the list of images and find the ones that are bad and unclick it in the list. Okay? There are a bunch of settings that we're going to go through. And we'll go through it in a minute, but you want to pick a situation here where you'll take the best 90% of the images. That means you're going to throw out 10% of the images arbitrarily. If you're very confident you have good images for every one of them, set that to 100%. Okay, if you don't want to bother checking each image, set it to 90%. Good chance you got 90% of them good. Okay. There's a long string of stacking parameter settings you want to check. Most of these are default. Like this one, we're going to do a standard mode of stacking. We're going to do an average for the light images, but we're going to do median for the dark images and for the flat field images. The median, you know what the median is versus average? Everybody know what that is?
Yes.
Okay, I'm not going to explain it. Well, if you don't know, tell me.
I don't know.
Okay. Median says you've got a population of numbers, and you look at all the numbers in the list, and you find the point in between the extremes that is exactly halfway between the maximum and minimum. Okay? That's the median. That's the point where the center of the population of the data. And it'll be an integer number, because the integer numbers are the data numbers that the camera produces. Okay? The average is you add up all umpty-ump numbers, divide it by the number, and the number that comes out is the average. And it will have a fractional part, typically. They'll be slightly different from the median in terms of absolute value. For the images that are the light images, you want the average, because you want to make sure you've got the best of the range of images you've got. For the median, for the flat field and the dark, you want the median, because that represents where the population is. Okay? And this is done pixel by pixel, mind you. So you got 10 flats. It goes through and looks at every single pixel in the entire frame and finds the median of each and every one of them. Okay? This is a very computationally intensive process. This is the easy part. Stacking and alignment is what really burns the cycles on the PC. Okay, you'll find that out very quickly when you start running this stuff. And if you have a bias and offset, it's the same sort of thing, median. You're going to do the stacking automatically. It'll select one of a number of different algorithms for what you're going to do for stacking. Unless you really know what you're doing, and I don't claim to really know what I'm doing, stick with the automatic. That produces pretty good images. You can start playing with this after you've had some experience. I typically default to using TIFF file images as outputs from the software. If you're doing scientific work, the FITS images are something you really want to be using, because that's what all the people in the real world doing science are using. There's fundamentally no difference between an uncompressed TIFF and a FITS image, other than the fact that the FITS image contains a great deal more measurement conditions information, whereas the TIFF file contains only basic stuff. And that's really the only difference. For nice pictures, the TIFF works just fine. And TIFF will work in 8-bit per bit per color, 16-bit per color, 32-bit per color. It has complete compatibility with anything you want to do. Okay, in the cosmetic list, you don't have to do this right now. At some point when you're processing your images, go in there and make these adjustments. To the detect and clean remaining hot pixels. The hot pixels are typically removed mostly by the dark frame, but not all of them. So this software will crawl through and find the remaining hot pixels, and you'll set these values. A number of people have used them. I've adopted them. They seem to work pretty well, but don't be afraid to change them if you want to play with them. Same thing with the detect and clean cold pixels. These are usually pixels that are pretty much dead, that don't respond to light at all. And you should be able to get rid of those before you do any serious stacking. And that's what that set of parameters does there. So that's the only thing you really want to worry about here in the cosmetic issue. The one that we really want to worry about is the output. This comes already defaulted. You go down here and you want to create output in and click on this file path line. You want to set that to deposit the final image after stacking somewhere in the same folder set as you have your images, so you don't lose it. I've had several instances where I forgot to do that and I couldn't find it, and I don't, what the heck was that? Then I went back 2 months ago. I took pictures and it was the same pointer in there, and that's where my new images went. Okay, that can be quite frustrating. It doesn't do any harm, but anyway, this bottom thing is checked automatically. It's use all available processors, and believe me, you want to do that. This machine has 2 cores and 4 threads. It's really, really slow for this kind of processing. My desktop has 8 cores, or 8 threads and 4 cores. What takes an hour on this machine takes 10 minutes on my desktop. And that'll give you a clue. I'm not going to go through the stacking on this machine. We're not going to sit here for an hour waiting for it. Okay. After you've clicked through all this stuff here, you click OK, and you'll get a final check on what warnings might be there in your setup. Sometimes warnings are irrelevant because you know you didn't do something a certain way. For example, you might have taken your dark frames at a different ISO number than your light frames. You might have accidentally done that. That may or may not be a problem. You should watch for that at least. Okay. And now for the processing. I think at this point it's better to just bring one up and go through it on the machine, because for me to stand here and wave hands about what to do is not very effective. So if you've got the data files, you might want to bring up Deep Sky Stacker, and we can go through this. Okay. I have previously stored a stacked image. If you go to the data we have in the DVD, I have a folder called Output Files, and there's an item autosave. That's the Orion Sword image that has been stacked but not processed. So we're going to open that image.
The image files?
It should be in the DVD I gave you.
Image files, picture files? Yeah.
You got it?
Which one is it? Image and the image
Autosave is the image that has been stacked but not processed. And it's also 32 bits per channel. So it's a big, big file.
files? Yes, out. We don't out. The image files, there's no output files.
What is it
There's
called?
Dark files, flat files, picture files, and NGC for
It should be in there. I'm pretty sure I set that up. Well, okay. I'll have to double check. Maybe I did forget it. Okay, so we're going to go down here. We're going to open a picture file and navigate to that folder.
So we're going to open a picture files?
I'm opening an autosave file that I stacked. It should be in your disk somewhere. I don't know if it was the same file names, but it could be under the name of Jupiter, autosave Jupiter or something like that. Autosave Orion Sword.
It's under image files and Orion Sword output files.
That's it. Okay.
Yeah.
So this is loading very slowly, and you'll find it will, because it's a big file.
Which one?
Orion Sword output file.
How many files being stacked?
There were 32, I think it was, sub-exposures that were stacked to make up this image.
Minutes of subs?
They were 2-minute exposures, sub-exposures.
Thank you.
Jupiter stack.
Jupiter stacked? Is that what the file's called?
That's what we got. Jupiter stack.
File.
No, not Jupiter. Orion Sword stacked. Or should be autosave. I forgot what it's called. I don't have an optical drive on my machine, so I can't look it up.
Open picture files or open something else?
It won't be in picture files. It'll be in another folder.
Yeah, but we open picture files.
Well, you got it. No. You got the contents of that.
Yeah.
Yeah. Oh, you open a picture file down here.
Yeah.
Yeah. Okay. So it's going to take a while to load the picture because it's 32 bits. Oh, okay. Thank you. Okay. Now, one of the things that's characteristic of this image is I took it from my backyard, so there's a lot of light pollution in it. That's why the gray appearance in the dark sky area. We're kind of doing two things at once here, but that's okay. So, if you click reset, it will bring up the default log square root stretching function that's shown here under all the colors. And you'll see that the green and red channels are pretty closely overlaid, and the blue channel is suppressed a bit. And that's in part because of the fact that I had a light pollution reduction filter, which kind of suppressed the blue field a little bit. So you go over here to the slider that's on the blue, and you drag it, whoops, to roughly overlay the rest of them. It doesn't have to be really precise. You want it roughly on top, like that. Okay?
We
If-
can't find that file.
Oh,
Yeah,
God.
The only file is Jupyter Stack. I just searched for standard tip.
All right. Let me, someone have the,
do it on one
on the folder that's,
Yeah.
that was in the,
Yeah,
you got the folder that was in the DVD?
yeah, this is what we got for the budget. This is exactly what I want to do.
Go to the image files. All right. Oops. Oops. That was a big oops. I think I probably didn't put it in because I thought we would go through the whole process, and I realized that's crazy. We can't do it. All right. We're just going to have to take it as it is here. You first make the small color adjustment. If the green and blue aren't overlapping, in other words, if you've got a light pollution dominated image like this, you're going to have errors in the positions of the colors. That's going to occur naturally because of the stacking process. You just want to overlay the histograms approximately. It's not critical. There is a box down here that says linked settings. You put a check mark in there because everything we do from now on, we want done to all color channels at once. Okay? Now we go to the tab here that shows illuminance. We click on that. That lets us adjust a series of sliders that controls the shape of this stretching curve. So this horizontal axis is the brightness scale that is represented in the image itself. Okay? The output is in the vertical axis. So anything that is essentially along this part of the line isn't going to be changed at all. Anything that's going up this slope is going to be radically changed in terms of brightness relative to the input. So in other words, as we move along this scale, we're slowly brightening the output for this particular data number. The data number under the pointer there is the actual data number in the image. The data number in the output is higher. Okay, that's a nonlinear stretch. And that curve represents what's actually going to happen. Now, that looks pretty extreme, but that's not as extreme as we want it. Say, what we want to do is not change the darkness much because we don't want to modify that a lot. And we don't want to make too radical a change in the bright level because it'll bloat the star images to being big round circles. What we want is the transition through roughly the middle of this histogram to stretch the most. So what we do is we grab a hold of this thing and we move the sliders to change the slope and the position of that curve. I know from experience this must be about 2. So the position is 2 here, and we want to put this guy, the steepest part of the slope, right in the middle of the histogram. Okay? So the nebulosity in here is mostly contained in the middle of the histogram. In this case, it's because of the light pollution, not so much because of the image itself. You wouldn't necessarily use this stretching function if you were in a true dark sky situation, because then the histogram that you see here will be sitting right about where the pointer is. So you use a different function for that to do effectively the same thing. Okay? So now, once that's set, the problem with this DSS is you cannot see what that function is going to do. You get an image processing package like Nebulosity or any of the others, Nebulosity is one of the least expensive. They will show you, as you diddle the curve, it'll show you what this image is going to look like.
Preview.
It's a preview. It's not a precise preview, but it's at least gives you an idea what it is. This doesn't give you a clue. So I'm going to click apply. Oh, wait a minute. I'm going to flatten this out a little bit. You see what I've done? I'm trying to minimize the brightening of the star images here. So the numbers you see on the screen are approximate. You'll play with them as you choose. If I click apply, it will do the processing on that image and you'll see what the effect is. You see a good deal more faint nebulosity coming out now.
If you had a photo program, Vance, could you just do it in there, or you want to do it here first?
You mean like Photoshop?
Yeah.
Theoretically, you could do this whole thing in Photoshop.
All right.
Okay? The reason I like to do it in this kind of a tool is you've already got a 32-bit per channel image, and it works in 32-bit. Photoshop will too, but the curves function doesn't work at 32 bits, I found out. It works at 16 bits per channel, but not at 32. And you want to do this kind of extreme stretching only when you have a huge dynamic range, because it'll avoid getting large gaps in the histogram, which will show up as steps in brightness in the image. And that's why I like to work in the maximum number of bits per channel as possible. When you stack the images, that's how you're going to end up with, at least with DSS, and most of the others work in 32 bits as well, because you end up with more flexibility in being able to process the image. So now you see a lot of the outer nebulosity of the Orion Nebula all the way out here. You see the Running Man starting to show up here. It's poor contrast because of the light pollution background. Yes?
So this is similar to the portion of the light pollution class, it's the same thing,
Yeah, it's the same thing, but
same
a
process.
little bit of history here. This was my first attempt at deep sky imaging in a light polluted sky. I chose this object because it's very, very bright. I figured if I can't get this, nothing else is going to work. Okay? So I got to this point and I said, geez, a lot of faint nebulosity is starting to show up in there. And as I'll explain in the next session, all that appears simple isn't. So I've already stacked all these images now, remember? We just took the images. They're separated in time by, roughly 2 minutes. Okay? So you got spread over roughly 3/4 of an hour. The image is taken in a sky that's light polluted. What I found out is the light pollution is time dependent, and it leaves a gradient as well. I cannot explain why it leaves a gradient, but I can explain roughly why it causes a time-dependent function to be present. And the reason is, in my case, I'm pointed to the south, roughly at the celestial equator for this object. I'm pointed out over San Gabriel Valley, where the worst light pollution is. All I have to have is somebody drive by on a neighboring street with their high beams on during an exposure. I've got extra light. Or somebody turn off a porch light in the back. Most of the time variable part of it is caused by changes in transparency. Because transparency is scattering light. And as the moisture precipitates out of the atmosphere, it becomes drier. The amount of light pollution that ends up in your camera is less. As you'll see next week, when we process the Rosette Nebula, the time dependence will kill your image if you don't compensate for it. And I'll show you how to do that. You can treat this as a dark sky image, and we'll just get rid of some things. You'll get gradients and even in dark sky images. So what we do here will be a useful tool even in a dark sky situation.
How long were the subs? How long were the subs?
These were 2 minutes.
2 minutes?
Yeah. 120 seconds. Okay, so we're at this point now where we have stretched an image, and if we like what we see now, we can save it, or we can go back to the beginning and start all over again and set the curve in a little different place. And I recommend that you get used to playing with it. Eventually you'll get an idea that most of the information is in the front edge of the histogram if you have light pollution in the image. When you're in a dark sky, you want to kind of put it toward the low end of the histogram. Okay? So don't be afraid of saying, that's not good enough, dump it and start all over again. It doesn't take that much time to do the stretching, but sometimes by experimenting you can get a large improvement in what you had before.
Which is the front end and which is?
Okay. This is the back end, this is the low brightness end of the histogram, this is the high brightness end of the histogram. It's very narrow because most of the data, most of this distance from 0 to here is light pollution. Okay? If this had been a dark sky, this whole histogram would be all the way back around here. And so you want to take the steep part of the stretching curve and you want to slide it along the back edge because you want to bring out the dim stuff. The front edge, you might go toward the middle. You kind of experiment depending on the object you're photographing. If it's a very bright object, you want to be toward the middle or even toward the front.
Can you make multiple passes on that?
Sorry?
Can you make multiple passes on that, tweak it, and then save it?
Yeah, but I don't recommend you do that. Yeah, you could save this and then stretch it again. But you're going to rapidly run out of smoothness in the image when you do this. We're not done stretching this, by the way. This is just the first step. This is the most extreme in terms of input to output light adjustment. You do that just to dredge up a fair amount of the image to begin with. We're going to do a lot more stretching in the photo processing tool like Photoshop, for example, or GIMP when it gets to be 16 bits. Okay?
When I was at Lockwood, I got images that, you're right, the histogram was way down
Yeah.
to the left. What curve, you say use a different curve for?
Well, let's take a look at what's available. Let's go back to the curves here. If you click on this, it brings up a list. If you click on the curve function, it brings up a list of curves that are available. And we're looking at the log square root. That's the one we're defaulting to right here. This is the second from the bottom. I have found that for dark sky images, the arc hyperbolic sine works better. If I click that, you see where the image goes? I mean the histogram goes, it drops to the bottom. It allows you to do some extreme stretching down toward the bottom. Of course, now the blue and the green are not lined up anymore because of what I did with the stretching. So I'm going to go back to the original image. Let me just do that. Let me just close this out and start all over again. We can talk about what comes up. So if we, oops. Any of these functions can be used in a dark sky situation or in a light polluted sky situation. I found that the log square worked pretty well. It's not the only way to do it. You can play with it. I'm kind of lazy. Whatever defaults come up in a new tool, you're usually pretty good to start with. And once you start to learn the tool, then you can start to experiment. And I strongly expect that you will do a lot of experimenting. Because if you don't, you're never going to learn anything. So now if I go back after this thing finishes loading. And needless to say, this loads a lot faster on a machine with faster processors.
Is that an old computer?
Sorry?
Is that an old computer or?
No, it's brand new.
Okay.
It's the same. It's exactly the same machines we use up in the dome with the planetary imaging. It's cheap. It's $300. Okay. It's good enough to run the auto guider and a camera. If it's not actually a DSLR. For example, if I want to use that QHY 178 camera, it's a USB 3. It's a USB 3 port on here. I can plug that in there and plug the auto guider into the USB 2 port. They'll both live together happily on this machine. But God help you if you want to try to do some hard processing, because this just doesn't have the horsepower. All right, so now let's go and select the arc hyperbolic sine function. You see what it's done to the way the histogram is set? You do a reset. Now, we got the same ordering change. The blue is suppressed a bit. And that's because of the filtration I had in front of the camera. I can make an adjustment on that to bring them roughly in coincidence. And we check the link settings. We go to illuminance and we play with it from here. Now, not much is going to change here because I'm working with a light polluted image, but if you're starting with an image that's good dark sky, sometimes arc hyperbolic sine works better. My experience has shown. Other functions in there will work a different way. It's a good thing to do, to go and experiment with them for a while and see what works best for your particular setup. Never depend on using the defaults forever. They're good to start with, no good to stay with. You need to branch out and experiment to make things better. Which brings up a point. I'm going to take a break in a minute. I'm suggesting that we might want to consider having a special interest group in LAAS for astrophotography. That we would meet here maybe every 3 months and discuss what we've learned, what things are a problem, have anybody else figured out a solution for it. We can exchange information. And believe me, I think it'll be really beneficial for me as well as you. Anybody interested?
Mm-hmm.
Okay. I'll see about getting that scheduled. I have to find out how to avoid colliding with other meeting times here like we had last week. Or I should put it this way, the board is going to figure out how to fix that. And I won't use names. Okay. So, let me stop here because we've got to the point where we've done the initial big stretch. And I'll go and we'll look at the image that's been stretched and saved as 16-bit per color. Because what I did here is we did the stretch, then I can save it as a 16-bit per color, then we can do the subsequent processing in, say, Photoshop or GIMP. We're going to use GIMP, and I'll show you what the images look like if I do exactly the same steps in Photoshop. But at least the sequence of steps in GIMP are exactly the same as what you'd do in Photoshop. Only difference would be that in Photoshop you can use layers as a way to build those adjustments. You don't have to use layers, but it's sometimes very convenient. It's a little harder to use layers in GIMP, but you can do it there, or you can just do it step by step. And I'll do it step by step first, and I'll show you how that works.
What was the name of that curve again?
Arc hyperbolic sine.
That's arc hyperbolic sine. Typically you want to use mathematically derived stretching functions because they're pretty well behaved. when you're using curves, they are not well behaved. So you got to be careful when you're doing that. Even though, as I said in answer to a question, can you do all this in curves in Photoshop? The answer is a simple yes. But you don't have real control over everything that you do here, like you do here.
Is that why you suggested to me that you do 2 sets of curves rather than doing it all at once?
Yeah.
Yeah, okay.
He had a question. He had sent me his image, and I played with it a bit in Photoshop and sent it back to him.
Yeah.
Of course, I failed to explain what I did. I'm sorry about that.
That you did eventually. Yeah.
But he noticed that I'd used curves twice, but very small changes. In fact, they
Right.
both looked exactly the same,
Exactly.
but they weren't. Because in Photoshop, when you use the processing tools that are in layers, you have the image at the bottom of the list, you have things that you can stack on top of it, different adjustments. And the way Photoshop works is it takes the image, the first adjustment on top of it makes a change to the image. Okay? The next layer above that makes a change to the image that was changed by the layer below, and so on, up the list. So a small change in the first curve stacked on another curve on top of it, another small change is a big change. And it's more complicated than that because I was making changes in different places in the image. And I'll have to show you that for it to make sense. But it's very powerful. But there's no control in the sense that it's so non-linear that once you get something, it's hard to repeat it. Whereas this you can repeat because it's an established mathematical function.
It's art rather than science.
Yeah, and there's nothing wrong with the art side of it because that's in the end what we're doing. The pictures are the art. Okay, can we get started again? What I've done is I started up GIMP so I can give you an idea of what the curve stretching process is all about. What I have, and I'm sorry I missed this stuff in your DVD, but we have this autosave, which is the original stacked image out of the Deep Sky Stacker. Then I stretched it the way I just went through before the break. That's saved as this thing is Orion's Sword 16-bit. That's that stretched image in 16 bits per color, ready to process in a tool that can do it. Now, when I load this thing up into GIMP, where it's going to be a window that's going to pop up a whole string of errors because it can't handle 16 bits per color, but it will convert it to 8 bits per color. And so we'll play with it there, and the steps I will go through are identically the same as what you would do with a 16-bit per channel image, except the resulting image from here is going to be fairly cruddy. And I'll show you what an image looks like processed exactly the same steps in Photoshop. Okay? So we start with opening a file. I gave you this version of the tools. It doesn't like that at all. Okay, there's the image. You'll see that there's a significant light gradient here. In Photoshop, there's that you can buy. I think it's Spencer. Do they charge money for that tool for gradient removal?
Yeah, it wasn't very expensive, about 20 bucks or something.
Okay. You can buy a tool that'll remove gradients. For this kind of image, though, I don't recommend it unless you're at your final step of processing and there's a remaining gradient that you want to remove to make a nice looking image. In this case, we're dealing with light pollution, and the light pollution is varying in brightness depending upon where you are in the in the frame. Remember, we have done the flat fielding. So that's not the cause of this gradient. That's actually in the light pollution. We stretched the bejesus out of this thing. So it's a very subtle amount of gradient that has been greatly amplified by the stretching process. So I'm not sure that even that tool that Spencer was talking about is suitable. You might not even be able to detect the difference because it hasn't been stretched. So we go to colors. Well, first thing we want to do is take a look at removing the gradient. The first thing we want to go to do is, where is the duplicate image? Okay, so I've taken the exact image and I made another copy of it. Okay, so that image is now active on the screen. It's absolutely no different from the original image. Okay, now I'm going to go to colors and tool, where the heck is it? Okay, go to filters, Gaussian blur, click on that. This brings up a window, let you play with this thing. The horizontal and vertical distribution of the Gaussian function can be asymmetrical. There's a link deal here that we want to keep linked. We want to go through here and set this to 250 and link the two together. Okay? So now what's going to happen is all the details in that image are going to disappear.
Was that linked to begin with?
The little link function here that I've highlighted here, that takes whatever I've typed into either one of these boxes and puts it in the other one.
But was it linked to begin with, or did you just?
No, it wasn't linked to begin with.
Okay.
Photoshop presumes you have a symmetrical Gaussian blur. This one doesn't assume that. I can imagine situations where it might be appropriate. Okay, so we will take that and we will apply it to this image. And when it gets through with its cumbersome and slow processing, you will see all the details disappear. Photoshop's a whole lot faster.
What version of Photoshop? Because I've got CS3 on my computer. Then I don't
It's
have
also
to- I don't have
Gaussian.
to- I
You look
don't
at
have to do a
filters.
month- I don't have to do a monthly payment on it.
Okay.
That's why I have CS3.
The Gaussian blur is under filters, blur, and then there's a list of blurring functions. The Gaussian blur is what you want. And it's in there,
Oh,
even in CS3.
Okay,
Yeah.
good.
That's an old function that's been around.
Yeah. Well, that's the program I got today.
So, you see what happened?
Ooh.
All the stars have disappeared. Unfortunately, the bright part of the nebula is still there. And that's not good. Okay, because that's not part of the light pollution. So, here's where it gets to be interesting. There is a cloning tool, if I can find it, because I know where it is in Photoshop, but I got to find it here. Here it is. Okay, what I'm going to do is set the size of the cloning tool to something huge.
Are you gonna subtract this?
You see how big that circle is? I'm going to clone from at least that size. I'm actually going to get bigger than that. Let me drag this over about 500. There. Maybe even bigger than that. You want this function to be, this circle to be almost the size of that bright region there. You see where the dashed circle is?
Right.
I want to flatten that out. I want to flatten this region out and this region out just a little bit. And I want to do that by copying out of the light pollution that's in this area. Okay. Wait a minute now. It's control.
So how big is that now, that circle?
On this one, it's 534. The exact number is not critical.
No.
You want it big. Okay? So, So we're going to copy from right about here, where the light pollution is about at its peak. And we're going to, we want to set the transparency. Where is it? Oh, opacity, here it is. I'm going to drag, come on. Oh, come on. I'm going to drag that down. It won't drag. All right, so we'll do it the hard way. Drag it down to about 50–60%. Because you don't want to, you want to be able to move that around while you're making the adjustments. So it's going to copy from the circle above into this region. See how it's changing it?
It works like Photoshop, very similar.
Yeah, it's similar to Photoshop, yeah. Then we're going to move it over to this region here, and we're going to reset the copy point. We're going to hit this one and this one. And this one here. A little bit more in this, well, it's, you know.
Sometimes you have to go back and resample once.
Yeah, well, yeah, that's
gets
probably a good
finicky.
idea in this case because we just have, I want to get rid of more of this. Okay, that's good enough for the sake of discussion. So now we have roughly a gradient image. We can play with this and get it a lot smoother. I'm used to doing this in Photoshop, so I'm having trouble with this one. So we're going to select all, and we're going to copy the image. We'll go back to the original image, and we're going to create a layer. New layer. Okay, the new layer. We highlight that, and paste. There's a new layer. Okay, so that's the way to do it. In the Photoshop, it's different. Okay, on that way. Okay, now we have the light pollution in the upper layer, the image in the lower layer, and we got the opacity at roughly 100%. We're going to actually reduce that to about 80%. Okay? The reason we're doing that, I don't want to subtract all the light pollution out exactly because I don't know how much of it might contain some of the other desirable features, so I'm going to do a little less than the maximum. Okay? And then we change the function here, the mode, to subtract. Okay? I've overcompensated it. Okay. Let's try again.
There's no undo?
There's not a good undo in this.
Oh.
That's why it's free. Exactly.
That's why it's free. You got it exactly. Oh, wait a second.
$10 a month. That's all it takes. Yeah. Actually, they have a subscription. It's $10. Yeah, this one. It's cheaper than mine. Upgrade to
Okay, try again.
it costs more. Yeah. So especially if you got the others on. Yeah, you spend £20 to 14.
There's two ways to make the adjustment to the brightness of the Gaussian blurred image for subtraction. I'll show you what that is in a moment. You can do that adjustment by adjusting the opacity, or you can use what I have done in most cases is I've used curves to change the actual brightness of the light pollution image. So what we're trying to generate here as close as possible to what is represented as the light pollution in the image. Or any other gradient you happen to have in there. It doesn't have to be light pollution. It could be a gradient caused by, clouds drifting through. You can get a gradient caused by that sort of thing. Or somebody shining a light in the direction of your telescope and you've got a gradient because of the reflection off the black lens hood of your scope. That's happened to me a few times. Okay, let's try again. Cut the opacity down a bit further. Okay. Okay, that's halfway close. Okay, now go to colors and curves. Here's the curves function again. If I go and set a point in the exact center here, and I drag that down just a bit, I get a dimmer version of that image. Okay, so I click OK. And then I select all, edit, copy, go back to the original image and edit, paste as a new layer. Okay. There. That got rid of the light pollution. Now we're left with an image to make a further adjustment. And we go back and the colors. Select curves again. If I had some not quite dark background, I'd select levels and then cut the black level a little bit. But you can see from the histogram there we have pretty much everything we need there, if you will. Okay? So, you see that little eyedropper?
Yes.
The eyedropper is a sampler. If I click in the dark area, that puts a reference point there. That says where the black area is. So if I hold down the control key and click that, it puts a point there. Okay? And if I go down here into the intermediate brightness nebulosity, and I hold down the control key, I get a second point. Okay? So now if I click the up arrow, I think I can do that in this one. It's not selected. Select the point, click the up arrow, and start to increase the magnitude of that a bit. Okay? Don't go too much at one time. You want to do this in steps, otherwise you end up with all kinds of enhancement artifacts. You want this portion of the curve to be fairly straight, even though it's slightly higher than the original curve, but you want that to, again, keep the bloating of the stars to minimum. So if we click OK, we've got a small adjustment, then we go back and do it again. And you keep doing this a little and a little until you get as much nebulosity as you hope to get out of it. Of course, when you're only working with 8 bits per color, it's hard to get anything decent out of it. Because we're stretching something that's already pretty limited in dynamic range in the first place, so we're going to get very little effect. But the steps are the critical thing. If you do small adjustments in curves, one after another, or in layers, as I said before, you can have a very accurate control over how much adjustment you do and in what areas of the image. You start with the intermediate brightness of the image, you make an adjustment to brighten that a bit. Then you find a region that's in a dimmer part of the image, and you brighten that a bit. And then if you need more, you'll pick another area that you want to work on, and you continue the process until you've brought out everything you want. Now, going back to the files, here's what you get in Photoshop by going through those exact steps I was talking about.
Do most of the buttons and whistles work similarly?
It's the same thing. Yeah, if you want to do it one layer, then another layer like I just did, it does that just fine in Photoshop. You can create a stack of layers in Photoshop. You can have, for example, the first layer above the image file maybe have levels, 2 layers of curves. Above that you might want to have some color saturation adjustment. Above that you might have some brightness adjustment. And you can play with all those layers little by little until you get what you want. And then when you've got what you want, you click flatten image, and it does all that processing, collapses it down to the file.
But you only make one adjustment per layer?
One adjustment per layer. If you were to do this like I was doing with GIMP, Photoshop will do the same thing. You go through one layer, make that adjustment, you finish it, you go through the next next curves function, you do that, and so on, one after another. If you don't like it, you can go back to the history list and blow away all your adjustments and go back and do them again. If you do it in the layers condition in Photoshop, then you can go back and make adjustments anytime you want. You can even save the image with all the layers in place. It'll be X number of layers times the size of the image you had before, because each layer has the same resolution as the image itself. So it adds up really fast. But if you don't mind spending a bit of disk space, you can keep your layers version so you can go back another time and play with it further and make other changes. You know, beginning where you left off or whatever you want. If you make the adjustments individually, then you have to go back in history and go back to the earliest part of the history that you made your change that you don't like, and go through the process again. The layers just makes it a bit more convenient to make adjustments. Now if you look at GIMP, there is a layers condition set up here, and I haven't used GIMP enough to know how to do it, but I'm sure you can probably do the same thing with GIMP. I'm more familiar with Photoshop, so I apologize for not being able to show you exactly how to do it here, but I'd be very surprised if you couldn't do the same sort of thing here. If not in this version, the next one. Okay? Okay, I'm not going to save this. As far as I'm concerned, it served its purpose. But the point is, if you go back and look at the files, and if I go and look at what I did with GIMP, you see what happens? You see that gradient there, that stair step? If I stretch things enough, it ends up putting this artifact in there that's caused by the fact that there's a very limited number of brightness levels in 8 bits. It's 256. 16 bits is 16,000 layers, or 65,000 layers. Okay? So it makes a big difference. You end up with gaps in the curve, and it doesn't make any difference when you're working at that level. The reason we got away with such an extreme stretch in deep sky stackers, we're working with 32 bits. It had no stepping effect whatsoever show up in the image at 16 bits. Okay? So that's the consequences of doing things with 8 bits versus 16 bits. Now the last thing, if we have time, maybe we have a little bit of time, I wanted to give you a little bit of a heads up on doing processing in AVI. Yeah. planetary image video clips. This AVI clip of Jupiter was taken with the little black piggyback telescope on the 8-inch up in the dome. It was done in a particularly good seeing night. You see how there's wiggling in the image? It's not a bad image already.
Yeah, it's pretty good.
Not a bad image already.
Hardly any video.
But there are 200 frames in that video clip. So what I want to do is use Registacks on that video clip to select the best of the images and then stack them to reduce the noise that comes with doing short exposures that you have with a video clip like that. The exposure time for that video clip was something like 30 milliseconds. So if you were to stop and look at one of those frames, it's pretty doggone noisy and not acceptable. So now if I go, and where's Registacks?
Was that shot with a color camera?
Yes, that
Okay.
camera in the dome is a color camera.
Okay.
So it's a full, a full color shot. Registacks. This is also a very computationally intensive process, but it's not too bad. Not as bad as what we had with stacking the sub-exposures. All right. Here's the Jupiter AVI file. So we pull it into Registacks, and there's one frame out of the set. So if we click set alignment points, it will automatically set a bunch of alignment points on there. You'll see them as red dots. Okay? Now, you might be tempted to put alignment points around the periphery because the edge is important, but be careful, because sometimes that will produce artifacts. So I'm going to just let it go with the defaults and see what it does. So we're going to click Align, and now it's going to crawl through all those images, finding the best of the images and align them so that those alignment points that are on the image are one on top of the other. Registacks will also make changes to the distortion in the image. You saw it was being kind of distorted. It will fix some of that too, depending upon how much. Okay, there's the stacked image, and there's a check here that shows you how much drift there was in the image during the video clip. If you click that, you'll see it's been moved quite a bit. Okay, that's not a problem because the alignment process has lined those images up one on top of the other. That's how far they move. It's bigger than the diameter of the planet. That's because the scope up there is not perfectly polar aligned, so there's a bit of drift. So now if I click Stack, it will stack those images that have been aligned, and this will take about 2 minutes. What will come out of that is a much lower noise image of Jupiter that's comprised of all the good images that were in that video clip. And the bad images were simply left out. This had an original video clip of 200 images. As I recall, it comes out 160 images that were good enough. If you have a bigger aperture telescope, that's a 120 millimeter aperture telescope. If you have, say, a 200 millimeter aperture telescope, you want to take a longer video clip than 200 frames. Because the larger the aperture, the more atmospheric effects on the image, and you want to take more images because you need a larger number of data set to select good images. Now this would have taken about 5 seconds on my desktop. Now the nice thing about Registacks is there are these wavelet functions that allow you to sharpen the image by working on the point spread function that's part of the telescope aperture. In other words, I showed you, remember in the previous lecture, I said that the point spread function is only determined by the size of the aperture of the telescope in terms of arc seconds. The physical size of that point spread function is determined by the F ratio of the telescope. Okay? And so what we're going to do, now you see the image there? You saw the video clip. Now it's a much cleaner looking image. That's not too bad on its own. Okay? I'm not going to save this, but what I would normally do is save the stacked image because we might want to come back and play with it again later.
What program would you go into after you get to this point?
I'm staying right here
Oh, okay.
because I can, yes.
Can you load, is there dark frames and bias and light frames within
There are not
Registacks?
because we're taking 30 millisecond exposures. There's not enough exposure time to have significant dark current show up.
And what would happen if you tried Registacks on
This?
a DSLR? If you had lots of...
Okay, that's a very good question. One of the limitations of Registacks is file size.
Oh.
Okay? So Registacks will have trouble with the DSLR that's being used as a video clip. However, there is a program that's also free called AutoStacker 2. AUTOSTAKKART
German.
2. German.
Yeah,
Yeah.
better.
Exactly. It works a lot better for big files than Registacks does, but it does not have any downstream processing like wavelets.
Okay.
You can stack everything, you can take the stacked image, you can crop it, and then bring it into Registacks to use the wavelets on it.
Okay.
But it does have a sharpening.
It does, but it's not very aggressive.
Maybe if you know what you're doing, I've never been able to get the wavelets in Registacks. I had taken an image of Saturn at home, and I did it in Registacks and tried to do with the wavelets, and I couldn't make heads or tails of how to get started.
Okay, let me give you some pointers on how to do that.
Yeah, I love that.
Okay, wavelets is a very powerful function, and if you overuse it, you get garbage. You can produce things that aren't in the image. What you want to do is adjust the wavelet processing to just improve the point spread function, but no more. Okay? And what you're going to get out of this image is not going to be any better than the aperture of the telescope is capable of producing under pristine conditions. That's the best you can do. Don't hope to bring out stuff that isn't there because of the aperture constraint. So in Registacks, you see there's a number of layers, actually 6 layers of processing you can use, and it depends upon the specific aperture of the telescope how many you need. For this image, 3 layers are enough. The sharpening function is what adjusts the point spread function.
That was an 8-inch telescope?
This was a 120 millimeter aperture.
Oh, 120 millimeters.
It's a very small telescope. You know,
5 inch.
under 5 inch. 5 millimeters under 5 inch.
Yeah, right.
Okay? The sharpening function is what does most of the work. The denoise function is what removes noise that's also enhanced in the process. Now, this is experience-based. This is what I'm going to show you may differ depending upon your specific equipment. But if you start with here, you have a 0.1, that's the default. If you backspace that out and make it 0.4,
0.4.
okay? It takes a bit of processing it actually does processing on the fly, so as you make changes. Now, I also found out that if you set the denoise at 0.2, it minimizes the impact of the noise on the result. You go to the next layer, you make that 0.3, and this also 0.2. third layer, 0.2. And 0.1. So you get the kind of flow here. The bigger the numbers in the sharpening, the bigger the numbers you need in the denoise. There's some up and down arrows that can make fine adjustments in those numbers if you find it's necessary. This is a hands-on process. There's no simple set of rules that says, if you do this, you will always get the right result. Okay? That's the problem with this thing. Now, there are sliders here. 3 sliders, one here, and one here. These are effectively useless because there's no change in here. Okay, those are basically, the sliders are at 0. So no processing is done at level 4, 5, and 6, effectively disabled. If I take this slider and I move it down about to here, you see what happens to the image?
Wow.
It gets considerably sharper. Move this one along. Likewise, it's a bit sharper still. And then this one I can move along about to there. And that's about as far as I can take it. You notice that the band has details in it now, which it didn't have before. Okay? If I turn off all these layers that I've just adjusted, I'll go back to the original image. Okay? So you see I've got a halfway decent image. I improved it with the first adjustment, made some finer adjustments with the other 2 layers, and now you can get the effect of the full resolution of that aperture, the 120 millimeter aperture. Okay? So if you get to the point where you're satisfied with that, then you click this thing that calls, what you're getting is a preview of the image here. It hasn't actually done anything to the image. If you click Do All, and what it'll do is go through the full process and chew on the image. Notice here
Moons.
that the 2 moons suddenly showed up after this processing. They were there before. But what I've done is I've peaked up, I've collected that energy that is spread out in the point spread function.
Third one.
Yeah, there's all 3 of them there. And has pulled it all together. These are effectively one resolution element in size. Okay? And all I've done is to do the processing so that those things concentrate the energy that was distributed into a more compact area. You can't see it too well here, but if we take this image, save it, and go into Photoshop, and look very carefully here, you see a very slight darkening of the background in the immediate vicinity of the satellites. That's where some of the energy has been taken out and pulled into the satellite image. Again, that's a single resolution element of the telescope, which is as tight as you can get it. No matter what you do, you can't make that any better. You can try playing with more aggressive adjustments to the wavelets, but all you'll end up with is garbage if you go past this point.
Would you do any adjustment to the color to make it sandier instead of reddish?
Oh, I do that in Photoshop.
Okay.
This is off color because of adjustments on the camera that took the images. If I'd done a better job of color balancing the camera when I did this was one of these things. We were sitting up there and we're looking at the images and said, no, that's pretty nice. So I clicked to record the video clip just to catch it. And then I played with it. It was a pretty decent image.
Beautiful.
Why now, so you only use this with planetary,
Correct.
and why not anything else, deep space?
You could. You can also do the same thing on deep space, but typically you're not resolution element limited in most of the things in the deep space images. You're limited more by the low light level than you are by the resolution of the aperture of the telescope. All you can do with wavelets in a deep sky image is make the star images a little bit sharper. That's not what you're after typically. It's the nebulosity, or you might use it, say, on, for example, on an image of a globular cluster. You might want to sharpen those stars. But you have to be very careful not to overdo it.
How about like something like a double-double?
Yeah, it would help on that to some extent. Yeah, absolutely. But for an extended object like planetary nebula, you're going to have signal-noise ratio problems more than you're going to have problems. With this image, once it's stacked, we had a very low signal-noise ratio. When you stack a deep sky image, you're going to have ranging from halfway good signal-noise ratio in the brightest parts, and rather bad signal-noise ratio in the dimmer parts, which you probably won't notice unless you zoom into it a lot. If you apply wavelets to something like that, it's going to look god-awful. I've tried it.
Alberio, would that be a good?
Yeah, it worked great on Alberio.
Could you repeat what you said about aperture and F ratio, what that affects?
Okay. The arc second size of the point spread function is only related to the physical aperture of the telescope. However, at the image plane, the physical size of that on the image plane is only a function of F ratio. The bigger the F ratio, the bigger that point spread function. The smaller the F ratio, the smaller that function. Okay? When you're doing planetary imaging, you want that point spread function to be bigger than your pixels. So you want to have a high enough Barlow magnification on your scope to push you into the realm where the pixels are significantly smaller than the point spread function. I gave you a little spreadsheet calculator that will take your telescope focal length and your F ratio and your camera pixel size, and it'll calculate the whole thing out for you and tell you how the spot size vary. The spot size is the term that's applied to the physical size of the point spread function.
How does that relate? I've seen the term image size, which is you're supposed to have a certain size, a certain number of arc seconds for your image size.
Scale.
Image scale, that's what it is, image scale.
Well, for deep sky objects, you're better off at being no more than 2 picture elements per point spread function.
Okay.
Because if you make it, if you magnify it enough to spread that over more pixels, your field of view goes down. So you got to play with it on your own.
Okay.
The image scale and arc seconds per picture element will affect the quality of the image you get. If you just start off with the assumption that you want to have about 2 pixels per resolution element, or spot size. The spot size is the point spread function expressed in the effective F ratio. The Rayleigh resolution is the size of that point spread function. So that little calculator will give you all that in a kind of a list. All you got to do is put in 3 parameters. Okay, it also will calculate your angular field of view for your camera.
Yeah.
I typically don't look at that because it doesn't matter. I'm more concerned about what the image scale is relative to the picture elements. And that's why I got excited about that back illuminated camera. 180 millimeter f2.8 lens has exactly the same image scale as the Teleview 85 at 480 millimeters on the SL1 DSLR. Exactly the same. And we'll see whether that really proves to be as good as it sounds.
That was the experiment you were trying to run.
That's what I was trying to run, and I screwed it up big time because what I had done is I'd used the side-by-side bar. The step I skipped was to remove the cone error in the angle of the telescope relative to the polar axis.
Uh-huh.
And it was so far off I couldn't find anything.
Oh, okay.
So I just gave up. Figured
So-
I'd rather spend my time working on the Takahashi
Yeah.
and getting that going. And that started to work, except we have backlash. And the auto guiding went crazy relatively quickly in the process, which reminds me to go back and to tell you, go back and check your backlash on your declination drive. If you have backlash and you don't fix it, the autoguider will oscillate in declination. And there's no fix for it until you get rid of the backlash.
Take it back to Celestron and have them fix it, or
I don't know how to fix a Celestron. I know how to fix an Ioptron.
Oh, okay.
Because you can take you can open the thing up, get access to screws and make that adjustment and get rid of it.
Okay.
The other thing about,
Something on YouTube.
yeah, the other thing about Celestron is they load the worm into the gear for the axis by loosening screws, pushing it gently into place and tightening the screws. Now, if you don't have a perfectly round and flawless gear, you'll get to a point where it'll be less meshed or bound up, okay? In Ioptron drives and several other manufacturers' drives, it's either spring-loaded or magnetically loaded into the gear. And it's pushed in there under a certain amount of force, and no matter what variations in the gear, it's still meshed correctly, and your backlash is gone. So you really need to work on that. You need to set up in your backyard, try to auto-guide it. If you get partway along and you start seeing this kind of thing in your declination curve, you know you're in trouble. You know you have a backlash and you've got to fix it. If you start getting, kind of a jagged curve that seems to meander around but stay pretty confined, it's guiding correctly. And that's what I wanted to show you in the field, but of course I couldn't duplicate the backlash except on the Takahashi, which had it. It hasn't been fixed. And that has to be one of the things we're going to do before we can give it to primetime use.
Yeah.
There is a procedure, by the way, for fixing that.
Ray said there's
Teleview,
something-
not Teleview, but Astrophysics actually published a information sheet on how to fix that backlash. The problem, again, by the way, with Astrophysics, is they have reduction spur gears to go from the motor to the worm. Ioptron and a couple of other companies use a belt drive, and they use a very micro-stepped motor setup to reduce the number of gears involved. So it eliminates a lot of the complication, if you want to call it that, with getting the backlash out of the astrophysics. Okay, that's about all the time we have. Any other questions?
I have a question. Okay, two questions actually. The Orion Nebula file that you had that we didn't have on our disks, can we either get it from you or can we generate from the files that are on the disk?
You can
already?
generate from the files on the disk.
Okay. Is there a way we can get that file from you so we can play around with it without screwing up the other?
Absolutely.
Okay. I need
Bring your machine over here and I'll come over there with my thumb drive and we'll load it in.
Okay, that'd be fine.
And if they kick us out, you can come back next week and I can give it to you
Can you
then.
email it? How big is it? How many gigabytes is it? That TIFF file. What's the
The
email?
TIFF file is about 160 megabytes, 16 bit per color.
Okay,
It's
well,
big.
you got it.
It's much easier if I give it to you
On
on your,
in 5 seconds. Yeah,
load it in
5
your
seconds.
machine on thumb drive.